All right, next. So those are the five things that waves undergo, right? Right? Reflection, refraction, diffraction, interference, and dispersion. Let's take a look at reflection first. Let's do a little simulation so you'll have an idea what's going on, right? Then you can see it. All right. So watch this here, right? It'll be a little delayed, but let's see if I can. Right. So I'm going to fire a ray here. I'm going to fire a ray on this mirror. Right down here. Watch here. And what you will notice is that when the ray hit the mirror, you saw it? Don't know how to go back, right? Back and do it over. Right? When the ray hits the mirror, right? You see have a reflected ray there. So if you look closely, this ray is the first ray. We call that the incident ray. Right? When the ray hit the mirror surface, it underwent something called reflection. Right? What are the characteristics of reflection? See this point here? So that point there is the point of incidence. Right? That there is your point of incidence. And as Anya was about to say, right? At that point, 90 degrees to the surface, we have a special imaginary line called the normal. That's okay? 90 degrees at that point there is called the normal. Okay? And here's the special thing about reflection. See this angle here? That angle there, which we call the angle of incidence. If you use a protractor on the opposite side here, that angle R, both of them equal. I and R equal. Okay? That is your first principle or your first law of reflection. The angle of incidence and the angle of reflection. Okay? This is your reflected ray, of course. So when an object, or sorry, when a ray undergoes reflection, right? When a ray undergoes reflection, the first law is that I is equal to R. I is your angle of incidence. R is your angle of reflection. Right, just do my little favor, draw a diagram. Draw a diagram and I'll give you a small. Right, draw a little diagram. The time, draw a diagram. What would happen if the angle is then changed? If I were to tilt this slightly, what will happen? It would change, but still be equal, right? But still be equal. Okay, so make sure you label it. I want to give you a note on what is normal and how to measure it, right? Right, so take a small note. Take a small note. Right, under reflection, the laws of reflection, number one. The laws of reflection. The laws of reflection. What are we could do? one that we can note. Right? So we can do this one. Right? Laws of reflection. Number one, the angle of incidence equal. The angle of incidence is equal. The angle of incidence is equal to the angle of reflection. The angle of incidence equal to the angle of reflection. And two, I want you to understand this, right? Imagine this, right? Imagine that this here is a plane. This is what I call a plane, right? So when they say everything lies on the same plane, they mean everything lies on this one sheet of paper. So imagine you have incident ray, your normal, and your reflected ray all lying on this one piece of paper. Right? So that's what I mean by one plane. Everything lies on this plane. The incident ray on this plane, the reflected ray on this plane, and the normal on this plane. Right? So if you were to look at them in a 3D diagram, they would be on one plane, all three on one plane. That's okay? So law number two, the incident ray, the reflected ray, the reflected ray, and the normal all lie on the same plane. Incident ray, the reflected ray, all lie on the same plane. They all lie on the same plane, right? So just know this, there's something I want to note. Note that the normal, note that the normal is 90 degrees. Note that the normal is 90 degrees to the surface at the point of incidence. At the point of incidence. At the point of incidence. And second thing that I want to always note, second thing I want to note, second thing I wanted to note is that the angle is always measured between the ray and the normal. The angle is always measured between the ray and the normal. So here we have three examples on board, right? We have to try to join number one, the normal, and number two, the angle of incidence over, and then we do the reflection. Right? So take a look at the first one. I will do the easiest one, right? I will do the easiest one. So this is the point of incidence, correct? And how you draw a normal again? In normal, not just up 90 degrees to the surface at that point, right? So your normal is here. Right? And this angle here is the angle of incidence. Everybody feel that? So therefore the reflection should be the same as this, right? So the reflection is right here. Okay with that? So you remember the normal is sometimes the hardest thing to draw. The normal is at the point of incidence, you're drawing a broken line because it's not a real ray, 90 degrees at that point. So B and C, I want you to draw a completely diagram. Be easy because that's the one that we just did on the simulation. See what you come up with for C. Let's pick this up. Just after the finish. All 5 and I can go correct. Right, this one, point of incidence, normal. What have that? Angle of incidence is between the what? The normal and the ray. So that's the angle of incidence. So the angle of reflection is same. Okay, try and make them look equal, right? Want to get this one? Want to get it? Don't put the arrow. Put your arrows, right? Put your arrows to show reflection. So put your arrows to show the reflected ray coming out, right? Right, well, please remember this because sometimes in questions, what it is do is that they'll give you the angle here and make it think that that's the angle of incidence, right? When the angle of incidence is here. Okay, look out for that, right? I checked, we didn't have any football. Like we are with huh? Yeah, somebody. Some football. Like we are with that chill. I saw two how by I saw Iron Man or somebody else. Yeah, the other. Are you okay with that? So those are two very important things. Once you can draw your normal and once you can draw your angles of incidence, it should be all right. Okay. All right. Online, are you okay there? Oh, I didn't finish this one. So here, and this is your normal. This is your angle of incidence, so your angle of reflection is here. Okay. Right, let us just try one little question. It might test your maths a little bit, that one. Figure this out, right? How much angles in a triangle? Like 2,000 of angles in a triangle. It's 180. Let's make it. Let's say here's 100. These are two mirrors. And I wanted to show me the part of the ray with all the angles, right? This is 30. Let's make it a little smaller, right? Let's say, let's make this smaller. Leave it at 100. All right. Let's see if we can. It's a little harder. It's a little hard. Sorry to give you a hard question, but I don't really have much question or reflection of yet. So here what I want to do. This is a ray, and this ray is incident on two mirrors, right? This is mirror 1, and this is mirror 2. Okay? This is mirror 1 and this is mirror 2. The ray will undergo reflection here and it will touch here. Right? And it will also undergo what here? It will also undergo reflection here as well. I want you to show me the parts of this ray and put in all the angles. All right? Take your time, right? Yeah, it should work out. It should work out. So you have two mirrors, right? And on the two mirrors, I wanted to show me I wanted to show me the part of the ray out. Okay, take your time. You can average the angle. Gotta be exact. You have to be exact, right? Take a few minutes into that. What the total number of angles in a triangle again? 180. And if here is 60, how much is here? If here is 60, how much is here? Here is 90, right? Here is 90. So here is 30. Okay, here is 60 and here is 30. Remember that, right? You'll need a little bit of information. All right, take your time and draw the part of the ray out from mirror 1 to mirror 2. Take your time. A little much going on here, man. Right? You do not see us, see them get way bigger than Texas. It's exactly great. Oh, that's what it's right. Like, So if here much? So if here 60, how much is here? Reflection, right? Here 60. It will do reflection. Let's see, here 60, how much is here? So here 60. And here. Yes. Okay. What are we just going to look at? Their triangle.
No, I'm not sure that this one side is better.
Right, so when you reach here now, you get it? Right, so we should have something like this. When it reaches here, it reflects. I just average it, right? Not that bad. Right? This is 60. This is 60, right? So if here is 60, then here is 30. 30 and 100 is 130. This triangle inside here is 180. So this angle here is 50. Right? But remember, this is a reflected ray. This reflected ray now incident on mirror 2. So what's the angle here? 40. Okay? And it will undergo reflection, right? So if here is 40, it will reflect here as 40. Right? So most of you all figure out the part of the ray, but in the angles, you just get that wrong. Right? That's where the maths will come in. All okay with that? And it can use a protractor. So because remember these bars, I just make it up. But you use a protractor and work out all of these. And you get this on this. Sorry. I didn't say you carry a protractor initially. But that's good. But that's basically concept there of reflection. You look same time. That's not on the sun and the primary schools just on that. I think the absent. So you so and then hold it less. I was going to be trying. It's in here, but that's all right. So next thing, everybody okay with that? So this is the first. This is your first. This is your first phenomenal wave reflection, right? You have diffuse reflection and you have other different aspects of reflection, but this is the principle behind reflection. Are you okay with that? Next one now is refraction. You will notice something about reflection, right? You will notice that the ray is staying in the same medium. Here's air, here's the mirror. So it's staying in air. But now, if we have a ray traveling from one medium to the next, like for example here, right? Look how nice it's looking. Right? Look how nice it's looking here. Right? Watch it here. Look in the same way. Now, what happened now is that the rays that will come into your eyes underwent refraction. So it's not really look bigger right here. Bigger and distorted because it's like that, right? But looking larger. Right? That is what called refraction. Because the ray is traveling air to water to you. So it's traveling through a medium. And they're two different mediums. So you're traveling water to air. Right? But if you go down inside the water and you watch it, right, it will look just like this. You gotta be inside the water, right? It will look just like this. But out in the air, right, it doesn't undergo refraction here because it's just one medium. But once it goes through a medium, right? Once the ray passing through two mediums, air and water, you'll undergo refraction. Any two mediums, right? Because what has happened is that the ray traveling at one speed in air. When it goes through here, it will slow down. And because of it slowing down, the path of the ray is not in a straight line anymore. It will change its path slightly. And by changing its path, the rays coming from this will be a little bit wider. So this looks a little bit larger. That's okay? Okay with that? So let's see if we can play around with this simulation here. That's not all. I know you want to put that very well. Hello? Okay, right. Come kids next. All right, I'll send it. All right, so there. Right, so you want to take a look at refraction, right? Let's see if this simulation here will work. Right, so there used to be this nice simulation, like you always see everything that I use a simulation from PHET, right? They have real nice simulation and physics classroom. Like if there's a topic into the kids don't understand, you can always go to them and just see how it works. And then put the little notes and formulas. All right. So let's take a look at this refraction simulation, right? Bending of light. Yeah, take this one. PHET is normally working best. This one I was looking for. All right, so what's this here? Look at this ray here, right? That's laser is generally what we're going to use to produce the ray, right? The ray is coming from air and going to water. So we expect it to what? To change direction, right? Slow down or speed up in the water. Slow down, right? So watch this here. See that there? Ignore the weakly refracted ray, right? We're not studying that at this level. We're focusing on the dark red ray, right? What you will notice here is that this ray, you have your angle of incidence and your angle of refraction is much smaller. See that? Notice, see I'm measuring my angles. I'm measuring all the angles between the ray and the normal. Right? And you will recognize that I is bigger than R. You okay with that? What you see, right? As I continue to move it, as I continue to move, right? As I continue to move it, see what happening there? Fractions still happening, right? But watch at this particular point in time. There's a particular point in time. A change in medium. We can't put it in glass. Right? So let's switch it around now. How to restart? Start, and I put it down here. I can't. Right? I just want to switch the medium. So I'm putting water on top and air underneath. to work on it. The ray that's coming out, what the ray undergoing there? The ray reflecting it? That's supposed to happen? No. So that's a special case. It's called total internal reflection. But if I make the angle smaller, see the refraction happening? Right? So I'm gonna explain what is happening a little while, right? See right here? This is I and this is R. So you're going from water to air. You're going from water to air. So the ray speeding up, and now you will see that I is smaller than R. You'll see that? So it's going the other way around now, from water to air. And the angle R became larger. Right? But let's just talk about the phenomenon that happened a little while ago. Right? Let's look at find it now. See this here? You will notice that the ray underneath, right? The refracted ray begins to disappear. You'll see that? And as soon as, watch it here again, right? Focus on the ray underneath. Focus on the ray underneath. See the ray on top light? Right? Watch this here. As soon as the ray underneath, the refracted ray hits 90 degrees. Look at the ray on top in the blue, right? In the water. And it's a little slow. Okay, getting darker and darker until all of a sudden the ray disappears. Right? See, at this exact angle here, we have something called that angle of incidence. It's a special angle of incidence called the critical angle. Right? That's called the critical angle. And when that happens, the ray no longer undergoes refraction. It undergoes something called total internal reflection. All right? Total internal reflection. Right? I'll give you a note on all that. I wanted to kind of just show you what happened, right? All right, let's go back to the first scenario. Right, since Nathan likes to use the protractor, right? Let's look at something special that happened. Right, Nathan, since you use the protractor, man, can you tell me what angle of incidence we have here? What's the angle of incidence here? I think best I could do it, yeah. Make it larger. How much? 30. Right? So angle of incidence, 30 degrees. Anybody can read off angular refraction? Who in front? Upside down. You can read it? I know it's not upside down, but you can read it. How are you looking like? About 22? About 22? Oh, the 20 here. 20 is that line there. About 22. So R is 22. Yeah? Right. Just do math paper. Go take a calculator and find sine 30. Find sine 30 and then divide it by sine 22. Tell me what you get. Sine 30 divided by sine 22. How much? 1.33. Correct? Yeah, everybody get up? Let's change the angle. Let's change the angle and tell me what you get. Let's go to 40. 40. Right? I is 40. And R is, I will help you. Looking like 25, 26, 27, about 28. 28. Do the same thing for me, please. Find sine 40 over sine 20. Tell me what you get. $1.3. Okay, let me change it to 27. 40 over sine 27. Okay, I changed 29. think about what's the exact value? 25.
Yeah.
Okay, we'll go with 29. You got 1.33. See that? What you recognize about the two values? They're the same. Well, guess what? There's a guy named Snell. He did the same thing. A guy named Snell, he did the same thing. He did this experiment and he took the angles and he found the sign of them. And he recognized that they all give you the same value. Right? And that's where he came up with Snell's law. Snell's law is? Snell's law tells you that sine I over sine R is the refractive index. Okay, so that 1.33 is the refractive index of all the atoms. Right? So that's basically what Snell came up with, right? Snell recognized that sine of I and sine of R. He recognized that that ratio is always the same, right? And then he called that ratio refractive index. Okay with that? That's refractive index, right? We can also find refractive index a different way, but I do not think, yeah, this simulation wouldn't show you it. But there's a next way for you to work out refractive index, right? You're okay with the concept of refraction? Let's take a little small note now. Let's take a little small note on refraction. Let's take a little small note on refraction. Right? Refraction is the bending of light. Refraction is the bending of light. As it travels through mediums of different densities. Refraction is the bending of light as it travels through mediums of different densities. The bending of light as it travels through mediums of different densities. Full stop. From a less dense medium to a more dense medium. From a less dense medium to a more dense medium. From a less dense medium to a more dense medium, the rate bends towards the normal. The rate bends towards the normal. From a less dense medium to a more dense medium, the rate bends towards the normal. So, how much the rate bends is determined by how much the rate bends. How much the rate bends. How much the rate bends is determined by its refractive index. Refractive index. Right? And if you write this, Snell's law gives the refractive index sine I over sine R. As I said, then the next thing you could do as well, you could also find the speed in medium 1 and divide it by speed in medium 2. Right, then draw this here now. Draw this after. Draw this, write the formula. For the SI unit per refractive index. What's the SI unit? Huh? Have none, right? Have none because it's a ratio. Right? It's a ratio. So it have none. No refractive index, right? No refractive index. Yeah, this one time open. Right? Finish? Right, so you're looking at the concept, right? So you're going from less dense to more dense towards the normal, more dense to less dense, you see it going away from the normal. Okay, so here we have two small examples, right? We need to find R, right? I gave you the refractive index you're using. It going from, let's say, air to water. And then I wanted to find R. So you know N, right? You know the refractive index, I know I. So you're using this relationship here and make R the subject of the formula. Okay? And here, you find N. Okay, for those who bad at subject at the formula, I want you to learn to practice this, right? N is equal to sine I and sine R. Two fractions equal sign, what you do? Cross multiply. So you'll get N sine R is equal to sine I. Correct? Trying to make R the subject, right? So you gotta get rid of N first. So you divide everything by N. So you'll get sine R is equal to sine I over N. So you want to make R the subject. So you have to move sine across. So R is equal to sine inverse. Remember, we're trying to make R the subject, right? So move sine across, and you'll get sine inverse sine I on N. So this is the formula to find R. Okay? So I'm going to start this, make it something very formula. So for the people who get trouble with this, well, you can kind of learn this version if you want. Or learn to make subject very formula. All right? I have a calculator, right? So you got sine inverse. I'll define sine inverse. Press second function sine, right? Sine I, which is 30 over. Should the angle be smaller than 30 or larger? Should be smaller, right? Should be smaller, right? It's going air to water, so it should be smaller. How much you got? 22.08. No, let me see that. 35.1. Well, if I straight in the class here, right? We'll check that and see. Please make sure you calculate in degrees, huh? For those who do extra examining this morning. Sine inverse Sine inverse sine 30 divided by 1.33, close that bracket, 22.0, 20.1. 22.1. Okay? 22.1 degrees. Online, all get up, Chelsea. Yeah, so what about, oh, you're working out here now? Without now. That's a refractive index, right? Right? Just find the refractive index here. Sixty and 20. 60 and 20, sorry. What you get a sine? Sine 60 over sine 20. 2 points. 2.53. Okay. 2.53. Yeah. Yeah.
Yes.
All right. So here's what we need now. We need now to get an experiment now to prove this. We want to prove that relationship there. We want to prove that sine I on sine R is really correct. Right? So there is an experiment called the glass block experiment that they use, right? I will start up here and you will finish it for homework, right? All right. All right, here. Right. So here's what it is. I know, try. Online only and they might hear, right? So here's what you want, right? We want to show that this is true. We want to show that sine I and sine R that is all equal, right? So here's what they did. You might do this in the lab, right? What you will do is you will draw a little normal and you will take two pins, pin one, pin two, connect them up, and they get it after that. Okay. Yeah. What you will do after is take two other pins and you're looking through the glass block, right? I'll show you that. at this glass block here. You're looking through the glass block. You're looking through the glass block, and you're trying to line up two pins. I'm on there. All right. Right? You're doing this next week most likely, right? You have a glass block, and you place the two pins here, and you have the incident wheel. You go and look through the glass block, and take this pin and try to line it up by looking through here. And when you line it up, this will happen. When you line it up, you'll get one pin here and the next pin here. And then you draw a ray. That ray is called your emergent ray. Right? Remember the objective is to find refraction, right? So refraction happening in here. What are you gonna do? You draw your normal here and you connect these 2 points up. So you're connecting up here and here. This here is your angular refraction. And you're going to take I and R and do it 6 times. All right, 5 times. And plot a graph. You're going to plot a graph of sine I versus sine R. Okay. So jot down what you need. We're going to do this next week. I want you to read up on the glass block experiment to verify Snell's law. Okay. So next week we are going to, I'll put it in groups like 1, 2, 3, 4, 1. We're going to go in 3 groups. And we will try this fast and find the angular refraction of this. Okay, now? So make a note of it. This is, I want you to pay attention to the emergent ray. This is your incident ray, and this is your refracted ray. Right? So for those who are online, you mightn't get to do it, but those who in person, I'll add it to somebody in person. Right? And we'll do this lab and calculate this and see if we can verify this. All right? So for homework, read up on this, read up on critical angle and total internal reflection. All right?